Ever heard the word idempotency and thought, that's just some fancy developer jargon? Well, what if I told you it's actually the most important crumple zone for all online systems? Stick around because by the end of this video, you will understand this critical concept and why it's the secret sauce that keeps your online world running smoothly. So why do we even need something with a name like idempotency? Imagine you're buying something online. You hit the pay button and the little loading spinner just keeps spinning. What do? You get anxious. You hit refresh. You click pay again. Behind the scenes, your simple action has created a huge problem for the system. Did the first request go through? Did the second? Are you about to be charged twice? This is the core problem: uncertainty. In today's world of distributed systems, where different services are constantly talking to each other over networks, messages can get lost, delayed, or duplicated. Servers can crash mid-process. Without a plan, this chaos would lead to duplicate payments, multiple orders for the same item, or all sorts of digital mayhem. This is where idempotency steps in as our hero. It's the system's way of guaranteeing that no matter how many times you retry an action, the result will be exactly the same as if it happened only once. Let's break this down with a simple metaphor. Imagine you run a warehouse. A delivery truck arrives with a shipment of goods. What's the first thing you do? You check your records. You look at the shipment's unique order ID and check it against a list of all the shipments you've already received today. If that ID is already on your list, you know you've already processed this delivery. You simply tell the driver, "Thanks, we've got this one already," and send them on their way. You don't unload the same goods twice and mess up your inventory. If the order ID is new, you accept the shipment, add its ID to your list, and then update your inventory. In this analogy, your warehouse operation is idempotent. The unique order ID is the key. Your list of received shipments is what we call a deduplication table in the tech world. The core logic is check first, then execute. This prevents the same operation from having an effect more than once. This is exactly how idempotency works in software. When your payment request arrives at the server, the system first checks if it has seen that unique transaction ID before. If it has, it doesn't process the payment again. It simply returns the result of the original successful transaction. If it's a new ID, it processes the payment, records the ID, and then sends back the success message. This brings us to the core principle of idempotency, the one-effect principle. It means that no matter how many times the same message or request is delivered, it produces only one single predictable outcome. Let's go back to our spinning payment button. Your browser might send the payment request once, twice, or even 3 times due to network hiccups or you hitting refresh. But because the payment system is designed to be idempotent, it sees the same transaction ID on the second and third requests. The system recognizes it's already processed this payment, so it doesn't charge your card again. Instead, it just says, "Yep, this payment was successful," and sends back the same confirmation message. The effect money being deducted from your account and added to the merchants happens only once. This is the magic. It transforms a world of uncertainty, retries, and potential chaos into one of reliability and consistency. This principle is the fundamental defense against the inherent unreliability of distributed networks. Now, here's the real challenge for engineers. It's not enough to just feel like your system is safe. You have to be able to prove it. How can you be 100% certain that an operation will neither be lost nor duplicated? This is what we call ensuring at least once delivery without introducing duplicates. Let's think about our warehouse again. What if the power goes out right after you've unloaded the goods, but before you've had a chance to write down the order ID on your list? When the power comes back on, your list doesn't show the ID. If the same truck, which never got a confirmation, comes back, you might accidentally process it again. This is the kind of edge case that keeps engineers up at night. Proving non-loss and non-duplication requires building robust mechanisms. It means your check and your execute steps must be atomic. They have to happen together as one indivisible unit. If any part fails, the whole thing rolls back as if it never happened. This is why creating truly idempotent systems is a deep and fascinating engineering challenge, involving careful design of databases, transaction management, and communication protocols. It is about building a system so solid that you can mathematically prove it will withstand the chaos of the real world. So let's recap. Idempotency isn't just jargon. It's a fundamental design principle that brings order to the chaos of distributed systems. It's the guarantee that repeating an action won't cause unintended side effects. We learned how it works using a simple logistics metaphor. Every request needs a unique ID, which is checked against the record before any action is taken. This enforces the one-effect principle, ensuring that retries and duplicate messages don't break the system. This is what allows you to safely click that pay button again without worrying about being charged twice. It's the invisible safety net that underpins the reliability of almost every online service you use daily. But building these systems is far from simple. It requires rigorous engineering to prove that no request is ever lost and no request is ever processed more than once. Understanding idempotency is the first step toward appreciating the incredible complexity and ingenuity behind the smooth, reliable digital world we often take for granted. We've only scratched the surface today. The actual implementation of idempotency can involve complex strategies like token-based systems, transactional outboxes, and different database locking mechanisms. Each comes with its own trade-offs and use cases. If you're interested in a deeper dive into how engineers actually build these systems, let me know in the comments below. We can explore specific patterns and even look at some code examples. Thanks for watching, and if you found this explanation helpful, don't forget to like, subscribe, and hit that notification bell for more deep dives into the tech that powers our world. See you in the next one.